slider.
Okay, we have that scope. So on top of that, it has a transmitting data at very high rate, like for example, 110 megabit per second, and it can ranges from 1 to 4 gigahertz. It is at the end, it is very low cost and low complexity compared to the existing medical diagnosis system. Okay, and it can be applied in this UW like short distance applications, enable wireless monitoring and other issues. Okay, as I say, that microwave-based system is a low cost and easy to use, lead to safer and most cases contactless. Okay, it is a non-ionizing and non-invasive. Okay, which I say contactless, penetrating and multiple times scanning as also possible with this microwave-based system. Usually the present technologies, it is a CT scan, okay, MRI, ultrasound and PET based scanning system, but CT scan gives us a maximum false negative and it is ionizing, you know. And MRI, we are not comparing with MRI, we try to give the solution in the like clinical level and even in the rural area. Okay, so although MRI is high cost and time consuming diagnosis process, like if any of you have experience to do MRI, it take more than 20 minutes, but if we use the microwave based system, it can take only a few minutes, like 4 to 5 minutes maximum. Then we do the post process and can provide the result. Ultrasound is a problem of like detect deep lying. Okay, if it has a deep solid cancerous tissues for other diseases, it has issues. And as you know, that PET also use the X-ray or imaging radiation, so rough complication for the pregnant women. On top of that, microwave signal can also give you a higher Tesla resolution. For example, like the MRI, usually the old days 1.5 Tesla they use. Present day, all the latest MRI machine can give 3 Tesla. Research level, some Germany university or research institute, they do 7 Tesla machine. But with the UWB, we can go even 10 to 11 Tesla because of the very wide bandwidth. So that means that UWB give us high resolution characteristics and give the accurate localization due to the penetration issues. So the basic things is like it has a, like if you see that we have some laboratory prototype, we can see that it has transmit a low level of microwave energy. Okay, from here it has transmit and different dielectrical properties such as like dielectric constant, permittivity and conductivity can be measured. Okay, by using the vector network analyzer. So with that different dielectric properties, we can detect the pool of blood or cancerous cell or usually cancerous cell is highly water content, 5 to 6 times to the normal values. So so from the dielectric properties, we can easily detect there is some ambiguous things happening in there. Okay. So this is the maybe future prototype, the head phantom. Before we go to the human model, we go to the some model like so you see the head phantom model surrounding with different antenna sensor, which you call in this case planar antenna, or sometimes we also use 3D or P5 antenna. So we collected a different data set from the different point. Okay, with for the transmission signal. Okay, then after that, once we get the backscatter signal with the vector network analyzer through the RF switches. Okay, that collected scattering data are processing by using the frequency domain algorithm or different algorithm. In that case, we can use the machine learning signals, the algorithm to collect the data. So, I don't know. I think there is some echo or some signals is. Anyway, what I want to say here, so the accuracy also depend on the antenna sensors, like that planar antenna accuracy, planar antenna performance is strongly influences to get the high resolution signal in microwave based system. So let's talk a little bit about what is a planar antenna and how can we improve the planar antenna and resolution of the signal. So usually we utilize planar antenna, which is included like a patch of multiple or variety of shapes. It can be rectangular, circular are the most common. You can see some of the example of planar antenna shapes like triangular shape. Okay, then some of the asymmetrical shape, and also we have different shapes which have a strong range of the efficiency signal we can get from by utilizing these types of planar antenna. Maybe go deep little bit some design, so maybe you can have some idea how can we improve the resolution by improving the performance of the antenna signal. Okay, for example, one example, like if we consider the side slotted Vivaldi antenna. So what we try to improve the performance of Vivaldi antenna utilizing the different stub angle. By controlling the stub angle, we can improve the lower level of frequency performance. Okay, and we can also, by varying the stub angle, we can increase the bandwidth. Okay, and by incorporating more slots, we can reduce the size of the planar antenna. So thus we can really miniaturize the microwave-based system. So it can be easily fit in the small places, even in a small clinic or doctor chamber. Like immediately, if you want to any of the doctor or clinician wants to detect or see what is the issues with the signals or in the head scanning system. Okay. Okay, so and we can see that this slot of the planar device antenna has a strong effect even in the gain and efficiency. So I don't want to go a lot of statistics here, like with the slot and without slot, how the performance can be improved in the efficiency of a planar antenna device. Okay, you can see that our proposed antenna, which we already published in different journals, like it has can go a very wide frequency, for example, from 1.5 to 7, and it is achieved even until 9.8 dBi gain, which is huge. So with the efficiency of 92%. And very efficient for the to get the high resolution backscatter signal from microwave imaging system. All right, if we see some pattern, radiation pattern, because we need the unidirectionality of the pattern signal to get a deep lying signal, to get the deep lying object or tumor or pool of blood to get it. So that's why we need a unidirectionality properties with that. So what we get from the antenna efficiency and from the antenna gain. All right, we have shown here a few results that which clearly match with our initial design and with the measured results. Okay, so by varying different, like even incorporating some extra radiator inside the back plane of the antenna, we can even get the fractional bandwidth more than 100%. Okay, radiation efficiency also can be increased with the directionality. So here the main features, by incorporating the extra slot or radiator, we can get very directional signals with a very low loss tangent of very low signal, loss tangent. Okay. And I also would like to highlight few methods that how can this planar antenna efficiency can be improved, thus can affect the microwave-based imaging system, and which can eventually give the better performance. Okay, like for example, if we use the if we use the metamaterial structure. Okay, if we use the metamaterial structure. Okay, if we use the metamaterial structure behind the planar antenna, it has a significant influence on the efficiency and the performance of the planar antenna device. So metamaterial is like an engineered material which is unconventional, which has an unconventional property. Usually we cannot get it in nature, the property of the material, thus we say metamaterial. So we come up with the property by engineering the structure, and we have to get, if we comply the metamaterial requirement, like negative permittivity and negative permeability. We can see here that if it falls the negative permittivity and permeability, then we can say it is a metamaterial, and by including this inside the device, we can increase the performance. So you can see this slide, the how we can measure the metamaterial property. For example, like we need to excite the metamaterial by using the waveguide. This is some example that how we excite by giving the low power from the vector network analyzer. Then we can see our desired performance, that whether it can false the negative region, the permittivity and permeability. Also, we can do some inside the chamber by using the far distance, keeping the waveguide. Also, we can excite and we can measure the metamaterial properties to control the antenna performance. Okay, we can see that like some frequency span, like for the metamaterial, another property is double negative property. If we can manage the double negative property within our intended region, then we can get more precise efficiency improvement with high resolution. For example, if we see that in this structure, we have the permittivity in the low frequency about, for example, 1.5 to 2.6, then 2.4 to 3.3, and 3.8 to 4. Okay, these double negative. So this will be our target to get the double negative in our intended region. Okay, same goes for like permittivity performance, also the negative values. And if we see from our the design, actually we try to increase the mutual coupling near the intended shape, like the meander shape. So if we can manage to increase the current density, then it will improve the coupling capacity. Okay, with the improvement of this coupling capacity mechanism, we can improve the efficiency of the planar antenna device. All right, if we go, okay, so these are few, okay. Okay, so how we can characterize the metamaterial property? We use Nicholson-Rose method. Okay, with this formula, I don't want to go deep on the math. So by calculating this refractive index and transmission coefficient method, we managed to get this metamaterial property, and we calculate the metamaterial property. Okay. Let me give you some more example, like even some metamaterial antenna can be designed from the split ring resonator. So if we can modify the concentric cross-shaped split ring resonator, this will give us more freedom to reduce the size of the device, okay, compactness. Okay, and then with that unit cell, I can show you some metamaterial negative property. Then only we can say this is the metamaterial, and then we utilize in microwave imaging system to get the backscatter signal. Okay, most of our design is published very high impact factor different journal to prove that it they also I mean that international reviewers also accept our concept, how we can increase the performance of and reduce the size for any compact devices. Okay, if we give this another example of like concentric cross line split resonator. So also what we do here, we do the cross line shape things to improve the performance. And if you look that we also get lower dimension like 70, but so far we use the commercial available substrate material. Okay, later slide I will also explain that we have started develop our own even the substrate structure to come up with these types of device. Okay, with the small size it is easily achievable even 7 dBi gain. Okay, by the technique here that we use the slotted dipole element with a finite array of concentric cross line split ring resonator. So original split ring resonator we have modified by using the slotted dipole element. Okay, and this is one example of 3D antenna which is utilized mostly. This PFAR 3D antenna is nowadays used in like a recent days a mobile phone like iPhone and other recent days smartphone. Okay, after we finalize this design, we go for like LPKF laser machine. We try to avoid the chemical etching because of the chemical effect. So we have this prototype machine in our lab, so we can go for the laser machine to come fabricate such types of planar device. Okay, and here are few example of properties that we can calculate, like the performance by exciting different port. We see that with our design, we have a strong influence near the port, and with the specific slot that we say the cross-shaped slot. In that slot, the strong influence of current give us more flexibility and more radiating parameter. And with that, we can get the unidirectionality of the signal from that device. Okay, so these are few parameters that we have measured in our Satimo near field measurement system. If you see, so we have the facilities like from the scratch, from the simulation, we design, we fabricate, we measured initial parameter, even with the latest state-of-the-art laboratory to fabricate these things, and we can measure the efficiency. Then immediately we can test it in our lab for our intended devices. Okay, as I think all of you, we know that we cannot directly test it on the human head. So before we go there, we have to test it in the head model. Okay, so by using we try to create some stroke like circular and rectangular shape stroke like with a different pool of blood of like few millimeter ranges from 9 millimeter to 12 millimeter, and we included our planar antenna, which in this case particular says the 3D or P5 antenna, and that we try to get the backscatter signal, okay, near the head, and we get the backscatter signal, and we can see the performance. Before we come up with this model, we also did some measurement in simulation state. Okay, I will not go deep with the values, like we have in different frequency range, and from our observation we found that to penetrate the skull and to penetrate the heavy boundary like a skull, it is better that if we go lower EWB range frequencies. Okay, and we also see that the performance without metamaterial antenna performance and with metamaterial, that it has a significant amount of improvement in terms of efficiency realized gain. We also tested the specific absorption rate, how much radiation come from there, and we found that our antenna with that complementary split ring resonator based with the metamaterial give us a lower radiation, or we can say specifically the specific absorption rate value. It has a two standard unit, like 1 gram tissue, how much the radiation return, and also the in the 10 gram tissue, how much radiation giving. And we found that it has a really some frequencies, it has give very small values of radiation return. So it is really safe to do in the medical or healthcare solution measurement. All right, so I will also maybe a little bit give explanation how we come up with our own head phantom model. So what we do, we fabricate the head phantom in our lab, like we have to come up with develop some pool of blood, white matter, gray matter for the to get the exact phantom properties. So what we do, you classify different component like dura, gray matter, white matter, and pool of blood, which we consider the stroke. And also with the component that we represent, what we do, that like we try to get the material like water, corn flour, gelatin, and propylene. So we try to get the same dielectric properties like that we have in the brain of a dura or gray matter or white matter. Okay, these are the few steps that we use in our lab to get such types of human head phantom. Okay, so and at the end, after we develop, then of course we cannot say that it is equivalent to the head phantom before we do measurement. So we do the dielectric measurement properties, and you see the equipment that with these dielectric property equipment, we try to get the exact similar value of the human head properties. Okay, with the dielectric value, I mean. All right, I hope I have enough time to continue. Okay, and Okay, so with that head phantom, we also get some different electrical property to maintain that we get the exact white matter and blood properties with along with the gray matter and dura matter. Okay. After we develop these such types of head model, then of course we go for the collected the signal. So we use so far different particle swarm optimization or optimization algorithm. Like one example, for example, like delay and sum algorithm we use, which actually involve two steps and to get the different point, and we map the point. Then also we have improved the delay and sum algorithm as a coherence factor delay and sum algorithm, where the weight of the signal or coherence factor rewards more coherent channel, okay, with the adjacent different antenna element. And we try to also incorporate the iterative correlation method, iterative correction. The extra time is adjusted by appropriately increasing and the distance that is considered here, the iterative correction method. Okay. We also we have also some further improvement on iterative corrected variation of delay, multiple, and sum algorithm. So we incorporate the iterative corrected variation inside the algorithm. Okay, these are the laboratory prototype that we have used to by utilizing our cross-shape metamaterial based planar antenna. Okay, what we do by using, you see the skull, that the model we use inside, we keep the head phantom material, and then after that, once we measure the dielectric properties and consider that it is equivalent the head model, then we have tested in different by utilizing like portable stand, and of course with the backscatter signal we measured by the power network analyzer. Okay, and then so we have different sector of, you see this multidimensional research. We have like antenna development, we have like image processing algorithm, and at the end we exploit these in the microwave based imaging healthcare solution system. Okay, so what we do for this specific test, that we use the 9 improved metamaterial based antenna, 9 antenna array element. We have also 16 array element. So based on our requirement complexity, and we can improve the signal strength. Okay, so for these cases, I've shown you here with this metamaterial based antenna, the nine antenna element is utilized for this measurement. All right, so we can see that minimum frequency we have started from 1 gigahertz to 4 gigahertz. I believe, yes, I have the, okay, you see that the system running condition. Okay, we can turn this with the 360 degree within a few minutes. Okay, then I think, yeah, okay. All right, you can see the measurement. Okay, data is collected, and yeah, so we can get the data, and then backend we have to do some post processing. Okay, so number of, for this case we have number of scan position about 50 and resolution about 1.8 degree of so number of frequency point goes 200. Okay, 201. So how we do for that n antenna element, that one transmit and other element is received, other 8 antenna is received, then second is transmit, then other 8 antenna is received. Thus it as also increase the resolution and the point. All right. Okay, so we are now working to improve this model. So maybe the final prototype will be like this. Okay, so we are working on this to how to go to the like clinical. So we are working with our hospital. Our university also attached, like Malaysia, most of the university is attached with the hospital. So our medical doctor researcher is coming giving us the input, and we are trying to improve in terms of the marketable product to place in the hospital to get the real data from the rehabilitation center of UCAM stroke unit. Okay, then we'll do some real sample. All right, these are a few tumor collect that initial scattered signal. From initial scattered signal, by utilizing different optimizing algorithm, we collected the tumor. Okay, we collected the tumor. All right, okay, so antenna head model with different stroke element in 4 different positions. Okay. All right. Okay. So we also or thinking not in the we don't use the portable stand. What about if we use the sensor in helmet. So to comply that helmet, to maintain that antenna, we have to come up with a flexible antenna. That means we have to develop a flexible antenna which can comply in the helmet. Okay, a group of people from Sweden, they are working on that. So what we do, we found that if we use the material, I mean that metamaterial or substrate from the commercial of the sale, there is no material is available for flexible things. So we come up with our own material, which is thiophene based, which is also another advantage of biodegradable facilities. Okay, because nowadays electronic waste is so much hugely increased. So you come up with some organic material to improve to comply these electronic waste and the flexible material substrate properties. Okay, what we do, like we can some therapin based material and then we make it a powder, and after the powder, by utilizing the sol gel method, we come up with the flexible substrate. So you see initially this is coming up like this, and then we go for as a powder, and then with the polyvinyl glue, we managed to get this flexible substrate. If we look at here, these are the equipment that we use, like XRD, and then the dielectric measurement kit that is initially. And before we go to develop the substrate material, even we try to look the grain size of the material by XRD. Okay, also the morphological analysis. If we see that if the grain size is small, then it has a better feature, and we have we can improve the dielectric permittivity from the material. And if we have the grain size bigger, then we have to go back for the different concentration of the material. Maybe I will show you some example of material that we use to develop the flexible properties to comply the requirement of helmet size. Okay. All right, we have also measured the loss tangent to make sure that it is not a lossy material. Okay, and we calculate here after we develop the planar device with the flexible property, that means flexible antenna. We also measured the size is very compact, like 14 by 18 millimeter of size of antenna. And also we calculate some antenna band condition, how the performance is degraded, and we found it is a very much within our range and ready to comply in the helmet. Okay, helmet carb side. Okay, if any of you have interest, so I can go a little bit about the synthesize. We have, like before we do the material of the thiophene based organic material. Now the recently we also start with the manganese zinc ferrite based flexible material to get the bendable capability. So as you see the process that we make the solution, then we make the gel powder, and then we go with the powder to come up with the our developed material. Okay, and if you see some results of like XRD pattern, how is if our peak can go the higher value, like for instance it here we can go 300, it has a better property to get the semiconductor material to comply with the high dielectric properties, as long as for the flexible material. Okay, so here I can show you some of the SEM scanning images by of the different concentration of magnesium, for example, like 40%, how it look like, and if we give the concentration of 60%, how will be the property. All right. You see that if manganese 40%, how if we make with the metamaterial based antenna, how is the property in terms of the reflection. Okay, then only if we get the better reflection capability, then only we can go the healthcare microwave based imaging system. So of course we also found that permeability, that which is a negative value, which is the prime requirement to say as a metamaterial, and it also come up with the lower frequency, which is also comply the UWB frequency, I mean UWB band, and of course the what is called the flexible properties. Okay, I don't want to go deep, like we also consider different band, for example S band, C band, okay, and the next band. So I want to show you here that even high frequency, also these types of flexible material can work properly. All right, this is one example of planar antenna, which will be incorporated in the helmet, okay, by the flexible property. All right, okay, so here we can see the permittivity as parameter value, like the permittivity and permeability, okay, which is negative with the magnesium of 40% of concentration. All right, so I'll not go to more slides on that. So you can see that we can clearly see the double negative properties with our developed own material. Okay.
Professor Islam, could you please finish within a few minutes?
Yes, I thought that I have time until another 10 minutes. Okay, anyway, I will finish by next 5 minutes. If you consider 45 minutes. Anyway.
Because we should have some question answer session also.
Okay, so it is included for, okay, all right. So these are the XRD properties. As I said, that if we have the higher peak, it has a better values. Okay, this is the grain size. All right, and okay, these are some examples. Okay, you see, then after we develop this, with this flex, you see, it is easily can be fit in the helmet, okay, the card position. All right, there is some measurement result that with this bendable condition, and okay, so you see that previously it was a different type of head, and now we can even fit this in the helmet. All right, okay, so we can precisely detect some image with tumor and without tumor. All right, so this tumor detection can be also done by using the deep learning method. So what we do, that we collected the images by using because usually microwave based signal is 4 or 5 images or 25 maximum by using different method. By using the augmented, we managed to get more sample, and also we implement segmentation model, which is a unit based. As we come up with, we try to reduce some layer on that, and it is improve the performance, which we give the name of microwave segmentation neural network model. Okay, and then we precise the what is called the tumor. All right, so not only head, even we have experimented in the breast imaging tumor. If breast tumor or any early stage of tumor, we can detect with this microwave based imaging system. Okay, almost similar method but different, because the present day, like most of the patient, they don't want like the contact based method, and also that during pregnancy time the ionizing radiation is an issue. So if we can go the microwave based system, then it has no contact. Okay, so it is called non-imaging. Okay, and contactless, and it can be detected in early stage of the tumor. I have almost, so our plan to, with the flexible material, we can go to the enabling home monitor with the flexible antenna, with the bra system. Also we can have a plan to measure the tumor. Okay, in the lab based, we can see that so far we have done with the phantom. This phantom we have bought from Japan, and we have tested. Okay, different tumor, and also we have developed our own model, breast phantom model with the different multiple size of tumor and multiple tumor. Okay, then we also develop homogeneous and heterogeneous tumor to detect the signal. All right, by utilizing our algorithm, we can easily detect it with even 2.5 millimeter size. So in conclusion, I would like to say it is of course low cost, no unwanted compression. So it is called non-invasive system. Of course, as we use the microwave signal, so it is non-ionizing. Okay, so it can be detected stroke or tumor. Okay, that's all. These are the references I have used for my talk. Okay, thank you very much.
Okay, thank you, Professor Islam, for your wonderful presentation on metamaterial-based planar antenna design. From very basic principles, you covered everything, including design aspects, material types used, and the simulation setup, experimental setup, and with all results and summary. You have discussed everything. So we are very much enlightened with your talk. Now I would like to conduct the question answer session to Professor Moshul Haq. He is the current chair of IEEE BTS. Thank you, Professor Moshul.
Okay, thank you so much, Professor Haq, for your nice conducting the session. So, hello, Professor Islam.
Hi.
So, I'd like to request the audience now for there any query, questions, and comment. So, the audience, if any questions and comments, so please feel free to ask to the presenter. So, maybe okay. So, there is a maybe query. So, please introduce yourself first, then ask the question directly to the presenter. Thank you.
Thank you, Professor Islam, for your nice presentation. We are enlightened, actually. Okay, Professor Islam, could you please share, stop the screen share so that we can see your face?
Okay. Okay. Is it okay now?
You can turn on the video, actually, no problem. Yeah, you can stop the screen share, or you can turn on your video.
I stopped already the screen share, no issues.
Yeah, it's okay, it's okay.
It's okay.
Okay. Thank you very much for your nice presentation. I'm Professor Yusuf, working in Jangin University. So my question is, I have worked almost 15 years ago, 2007, using MRI machine in South Korea, which was 1.7 Tesla machine. Now you are using 9, 8, or 11 Tesla MRI machine. And your image acquisition, I have seen 360 degree, and you are collecting 50 equal points of 7.2 degree each. So my question is, if you decrease the each rotation degree, for example, 2 degree, then you can take 180 slice. So what do you think, if we increase the slice, or if we decrease the degree duration, can we get more detail of the images during the image acquisition?
Okay,
What is your comment, please?
Yes, excellent question, and I'm happy to know that you are working on MRI. Yes, initially, actually, people work with the MRI images, and then it has. And nowadays, in microimaging, not actually new. A lot of researchers now start doing, like, for example, one group of Germany, they also start working on that. So yes, as I mentioned, if you recall that the specification that you mentioned, it is only 9 antenna element array. Okay, with that resolution we get. So if we can increase, and also I mentioned that we also have a setup of 16 antenna element. Okay, so if we increase the antenna array element, then you can have a more control on the image resolution and the point. So what I talked about the things, like my initial target is to make the device compact in terms of the and improve the resolution capability, not increasing the number of antenna element. You got my point?
Right,
Yes.
right.
Yeah. So this is my research.
Thank you so much.
So if we increase 16 element to 32 element,
we have to. Yes. I got your point. Thank you so much.
Okay.
Okay, any other questions? So maybe Professor Mamun is waiting for us to ask the request question.
Thank you. Professor Islam, is a very nice presentation, and it's a new window for medical science to disease diagnosis. I'm wondering that we actually clinically validated CT, MRI, PET, or other things. And every technology have a benefit and their side effects. We know microwave have a human hazard, but it is sometimes in tolerable range. That's why we are able to use phones for a long time. So did you had like opportunity to look into the health hazard of using this microwave technology for stroke diagnosis, and what are the challenges? Thank you.
Okay. Thank you very much. Very interesting question. Yes, yes. You know, sometimes I have to give a talk on how is the health hazard things. So if you look back my slides, I don't know, I have stopped the slide. That one measure I have put like a specific absorption rate, which is called SAR. Even in the mobile, it is mentioned. Okay, and International Health Organization given 1.6 watt per kg. Okay, so we have to comply that. And even in my study, I have shown that this microwave based technology, because we are using the very low level frequency, even not in the mobile range, which we call EWB. Okay, and it is also, I think one of the slide I show like minus 40 dBm. Okay, and it can go even minus 140 dBm. So very, very interesting actually. Yes. So with that UWB frequency, we can reduce further. Okay, we reduce further, and it is very early to comment like whether it is comparable with MRI, because MRI has a different, different level and established. But what I want to say here, like lot of patient and MRI, I think in Bangladesh it is about 8,000 to 10,000 taka to do the measurement in hospital. Even big hospital you have to go. So our target, like to do it in the clinical environment, like even in the clinic. Okay, and even MRI, you need a very big places to include, and it is taking 20 to 30 minutes. So what I want to say here, that any initial diagnosis is very much possible within a very short time, even in the doctor's chamber.
Okay, thank you, Professor. So maybe Professor Manu has another question, but I cannot allow him due to the time constraint. So maybe, yes, maybe he talk in another time in more detail. So due to the time constraint, we just allow the one more question. So this time, Professor Arifin maybe ask the one question.
Okay. Thank you very much. Actually, no problem. Thank you, Professor Tariq. Actually, it's a great contribution, and I am not directly related to this domain. Probably Professor Moshiol read that I'm going to ask the question. Anyway, I'm thanking from the organizing point of view. As a TPC chair, it's our pleasure to have you with us in this very effective, and that we hope it will make a big change. Our Professor Mamoon, actually, he is also working in this side. So I think it will be huge benefit in coming days. No question from my side. Thank you.
So thank you so much. So we are extremely sorry because this is the last time, already 15 minutes past. So there are lots of questions from the audience, which is very, very interesting and enjoyable topics, and also the important in the healthcare point of view. So from the audience, so I'd like to thanks to the all for enjoying the session, nesting with us. So I'd like to hand over the session to the another session chair, Professor Muhibul, and also the moderator. Maybe we request Professor Tarek few minutes stay with us for the crest or certificate and our session.
All right, all right.
I think we can hand it over to the session moderator for conducting the next part. Yes.
Thanks. Thanks to Professor Dr. Mohammad Tariqul Islam sir for providing us your valuable presentation. It was a wonderful presentation. So now I would like to request our session moderator, Professor Dr. Mohammad Selim Hossain sir and Ratandeep Puri sir, to hand over the crest to our session chairs.
And our session chair, Professor.
Thank you. Thank you, Professor Islam. It was a nice presentation. We are at the end of the sessions. Before concluding the sessions, we have a ceremonial session. I will hand over a crest to the keynote speaker, but in absence of you, we would like to hand over to one of our professors here. That would be delivered to you later, if you permit that one. So I am requesting Professor Chair of the session to collect this memento for Professor Islam.
Thank you, sir. All of you are with us. This is the president ceremony.
আগে একটা দাও ইসলাম keynote speaker যাবে ওনারটা তরিক ইসলাম দাও
So on behalf of Professor Tariqul Islam, I am receiving the crest. So organizing committee will hand over it to Professor Tariq later on.
Thank you very much. Thank you very much.
Okay, thank you, Professor Tariqul Islam, for your wonderful presentation. Thank you.
So next time to
Moshiul Haq, Moshiul Haq.
Thank you. So the time for having is it time group photo if you oh এটা দাও না তখন
কি ওরে বাবা এই ক্রেস্ট তো
আচ্ছা আচ্ছা
আরে বাবা এই স্যার একটু আসেন এই যে স্যার আমার মোবাইল এই আরে ঠিক স্যার আমার ওই উপরে চলে যান না না আরে ছবির জন্য বলছি এই আমাদের মোবাইলে করে আচ্ছা একটু উপরে আরে দাঁড়ান রে ভাই লম্বা আছে আরে আপনি জিতেছেন আপনি ধরেন
যারা উপরে উঠছে তাদের কবরের সময় হয়ে গেছে, যারা নিচে তাদের কবরের সময় হয়। তুমি বসো 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 হ্যাঁ গুড
okay thank you so that's the end of the session and thank you the volunteers for the tremendous jobs. Thank you everybody. Sir